Welcome to the first video in what I see as being a series of 3, where what I'm going to do is start with very basic concepts of calculating interests and going on to show you where the formula for calculating a mortgage payment comes from. That's going to be kind of the grand end here. Warning though, this video is going to be a very fast presentation. And by that I mean, I assume that you are already familiar with some of these concepts, at least a little bit, and I assume that you're pretty good at math already. If people want, maybe I can do a longer, slower version of this later, but this is designed to take people all the way in 3 as brief as possible videos from how do you calculate simple interest through compound interest, through formulas for the present and future value of annuities and perpetuities, to pricing bonds and calculating mortgage related things. Especially we're going to end with that mortgage payment idea. We're going to end up with kind of 2 formulas, and when we get there you're going to understand where the formulas come from, and you're going to be able to derive these formulas from scratch on your own, because you're going to understand all the concepts that go into this formula, which friends of mine jokingly call the Berkey United Formula for Asset Pricing, which is a formula that you can use to price all kinds of different assets. Not all kinds, but all of the basic ones in one big formula. And then at the very end, we're going to solve this formula for payment here. And this is going to be, how do you calculate a mortgage payment? So as always with my videos, I really highly recommend that you look in the video description and you download this PDF and you print it out so that you can work along with me. So again, in this video, we're going to cover simple interest, compound interest, future values. We're going to talk about this thing called the Rule of 72, which is a rule of thumb. We're going to talk about present values. Next video, annuities and perpetuities, and the final video, bonds and mortgages. Just a little bit of terminology before we start. If you invest money or borrow money, usually we'll call this initial money that you are either investing or borrowing the principal. The investor is going to earn money, or the borrower is going to pay money called interest. Normally, we think about this interest as being a percent, like 5%. But all the time, when you're doing mathematics with interest rates, you want to convert them to a decimal form of a percentage. So 5% becomes 0.05, 10% becomes 0.10. We're basically just dividing that number by 100 or moving the decimal place over 2 places. When we talk about present value versus future value, the present value just means what's it worth today. If you have $100 in your hand right now, the present value of that $100 is just $100. That's all we mean by it. Let's call present values PV for short. That's what we'll use in our formulas. Sometimes we'll also think of a present value as being the principal, like we were talking about above. So if I'm investing money today, then that money I'm investing you can think about as the principal. It's also the present value. If I invest money and wait some amount of time and that money grows in an investment, we call that the future value, and in formulas we'll represent this by FV. The last thing we need to do to get started is talk about the interest rate, and I'm going to represent the interest rate by R. Always represent this interest rate R as a decimal form when we're doing math. So if you want to calculate what we usually call simple interest, you put money in some sort of investment at the beginning of a year or the beginning of a month. Let's think about years most of the time. If we want to calculate how much interest we will earn over that year, the formula is just take the amount of the principal or the present value, multiply it times the interest rate, written as a decimal, and you get the amount of interest. For example, if we wanted to invest $100 at 7% interest, and we just wanted to calculate the interest on that, it'd be 100 times 0.07, or let me use parentheses instead of dots so that we can keep ourselves straight here. So 100 times 0.07 is just $7. Quite often what we'll want to do though is not just simply calculate the interest. We'll want to calculate the interest and the principal, the original investment added together. So when we do that, we'll do something like this: 100 plus 100 times 0.07. However, a much shorter way to write that would be to collect the two hundreds here and write it 100 times 1 plus 0.07. The 1 brings in the original principal, and then the 100 times 0.07 brings in the interest. So here's our first general formula. A future value, how much money we're going to have a year from now using just simple interest. That means there's just one period that we're calculating the interest for. That future value is the present value times 1 plus r. The next step in our journey is to use compound interest. Compound interest is when our money earns interest. We leave the money, the original principal, and the interest in a bank account, for example, and we earn interest on the interest. So this is called compounded interest. So let's just think about that for 2 years as the simplest case. What would we do? The idea, and we'll come up with an easier formula in a second, but the idea is to calculate the simple interest, 100 times 1 plus 12% interest here, so 1.12. And then that's going to give us $112 after 1 year. But then we're going to reinvest that money, leave it in the bank account, and that $112 will then earn interest for another year times 1.12. And then what we're going to end up with is $125.44. We don't just earn $12 in interest every year. The first year we earn $12 in interest. The second year we earn $12 in interest, plus we earn interest on the previous interest. That's the whole idea of compounding. So a shorter way to do this is to just take the original $100 here, multiply it times 1.12, and then we're plugging that in over here, and we're multiplying the same thing by 1.12 again. So a shorter way to write this is just 100 times 1.12 times 1.12 again, or times 1.12 squared. So here's our next general formula. If you are investing money in some kind of account, and it's being left in that account for n years, n could be 2 years, 3 years, 10 years, and it's going to be compounded, then our future value is going to be equal to the present value, the original $100 we're investing, times 1 plus the interest rate, and we're going to compound that n times, however many number of years we leave it in there. The next step in our journey is not all things are compounded just once per year. Sometimes you'll put money in a bank account and it'll be compounded monthly or sometimes even daily. So here's how to think about what's going on there. The first step is to calculate what would the monthly interest rate be. This 12% interest rate here is the APR, annual percentage rate. If we want to convert it to a monthly rate, we need to take that 12%, let's write it as a decimal, divide it by how many months are there in a year. We'll divide it by 12, and that gives us that the monthly interest rate is 0.01, or 1% per month. Then the second step is, okay, if this is being compounded for 2 years every month, how many total compounding periods are we going to have? Well, it's going to be 2 years times, there's 12 months per year, that's going to be 24 months, 24 times that this is going to be compounded. So to calculate our final answer, it's going to be the future value equals the present value, $100, times 1 plus the monthly interest rate, 1.01, raised to the number of compounding periods, 24. And what we're going to get when we put that in our calculator is $126.97. Basically, what I want you to see here is that the more often we compound, the more money we're going to get in interest, because we're going to have more often where we can earn interest on the interest. When we only compound yearly, we get $125.44. When we compound monthly, $126.97, a little bit more. Well, let's take this to the next possible step. Let's compound daily. Let's assume that there's 365 days in a year. We do exactly the same kind of thing. Our daily interest rate is going to be 0.12, the annual interest rate, divided by how many days in the year there are. And our daily interest rate is 0.000328877. The decimals keep going. Let's just round it off to 5 significant digits there. And then B, how many compounding periods will there be in 2 years if there's 365 days per year? Well, if there's 2 years, 365 days per year equals 730 compounded periods, 730 days in this case. So how much money will we end up with if we compound daily? 100 times 1.000328877 raised to the 730th power. And that gives us about $127.12. I'm going to add another couple of decimal places here just for something we're going to do in a second. So 016. And of course, depending on how many decimal places you round this daily interest rate off to, you might end up with a slightly different answer. So our general formula here, and we just to point out, we get a little bit more money when we're compounding more frequently. But here's our general formula. If you're compounding k times per year, our future value equals the present value times 1 plus the interest rate divided by k. So let's say k is how many times per year it's being compounded. And then we're going to raise that to the n number of years times k periods compounded per year. Now, what would happen if we take this to the extreme? In the limit, what happens as we compound more and more and more and more frequently? We see that as we compound more and more frequently, we go from $125.44, $126.97, and this is just about 15 cents more, even though we're compounding much more frequently when we go from monthly to daily. We're approaching a limit here. If we compound more and more frequently, the amount of extra interest we're going to get is going to go up slower and slower. Let me show you an example of how this happens in Excel. So here I had Excel help us by compounding more and more frequently. Here's a simpler example. We're just investing $1 and we're investing it for 1 year at 100% interest. What if we don't compound at all? Then we're going to end up with $2 at the end of a year. What if we compound twice? Once after 6 months, and then at the end of the year, we end up with $2.25. If we compound 3, 4, 5, 10, 100, 1,000, 100,000, and 100 million times, then you see that the amount of money we're going to end up with is approaching some limit here. And the limit that it's approaching seems to be around 2.718281. Well, the number that we're approaching is sometimes called e, the base of the natural logarithm, which is 2.7182818285, and so on. This is an irrational number. The digits go on forever, and there's no easy pattern to figure out there, right? So e, the base of the natural logarithm, turns out to be part of this formula when you're continuously compounding. Let's go back and let's see what that formula looks like, and then let's use it and see how much extra money we would get if we compound every instant. Future value equals our present value times e, that base of the natural logarithm. Again, it's roughly 2.71828 ... And we raise that to the interest rate times how many years we want it to compound. Now here, this t does not have to be an integer. Normally when we think about compounding, we're thinking about compounding a certain number of years or a certain number of days or a certain number of months. Here, this t could be 1.33 years, right? 1 1/3 years, for example. So you can plug in any number of periods here that you want to try. Now let's just do this for 2 years so that we can compare to our other results. So if we plug in $100 and multiply that times E and raise it to the interest rate, which is 0.12, and then 2 years, the amount of money we would have is $127.12. But then if we add another couple of decimal places here for 9. Almost the same thing that we ended up with up here, but we see it slightly larger, but not even a penny more, right? Almost a half a penny more if we go from daily to continuous compounding. All right, these next two questions I'm asking, suppose we wanted to invest a certain amount of money, $1, at a certain interest rate. Let's look at 6% and 10%. And let's just go back to compounding annually. Now, why compounding annually? Because we actually see that it doesn't make a whole lot of difference. A little bit, right? A little bit. $125.44 versus $127. A little bit of difference. General principle we're going to learn here applies no matter whether you're compounding yearly or daily or monthly or weekly or continuously. We'll get similar kind of answers. So suppose you wanted to know, how long do I have to wait? How many years do I have to wait until my money would double, or approximately double, at 6% interest? And then let's do the same thing for 10% interest and see how much shorter of a time it'll take for your money to double with a higher interest rate. And by the way, I'll link to this Excel spreadsheet as well. So let's put in the 6% interest rate first. And we're starting off with $100, let's say. After a year, 2, 3, 4, how many years does it take for the money to become $200? Well, about 12 years. Maybe slightly less than 12 years, we'd have around $200. Again, if it's only compounding exactly once a year, we'd have to wait 12 years. But if it was daily or monthly, maybe it would be a little bit shorter than that, right? So our answer is about 12 years if our interest rate is about 6%. What if our interest rate was 10%, 0.10? It looks like we would have to wait between 7 and 8 years. Technically, it'd be 8 years if we were talking about exactly compounding only once per year. Again, what we're trying to do here is look at an approximate answer, 7 to 8 years. So at 6%, we would have to wait about 12 years. And at 10%, we would have to wait somewhere between 7 and 8 years. The point of doing this is that turns out there's a very good rule of thumb, which is an approximate answer. And you can just carry this rule of thumb in your head and it'll tell you about how long do you have to wait at various interest rates to double your money. And it'll give pretty accurate answers, no matter whether you're compounding daily, monthly, or continuously. Pretty accurate answers, but not exact. And we call this the rule of 72. And there are different versions of this. You can go to Wikipedia and look at the rule of 72 to find out more details, but I'll give you an approximate answer for where this comes from and tell you most of what you'll learn if you look at this on Wikipedia. The rule of 72 basically says take an interest rate without turning it into the decimal representation, just the percentage whole number. And it says if you take the number 72 and you divide it by an interest rate, say 6%, but we're just using the number 6 here, 72 divided by 6 is 12. And what that tells you is it would take about 12 years for you to double your money. If we take 72 and we divide it by 10, if we have an interest rate of 10%, that gives us an answer of 7.2, which agrees with what we found by taking the effort to go into Excel and calculate it, that it would be somewhere between 7 and 8 years for our money to double. Very cool. So here's basically what the rule of 72 looks like. The time to double is approximately equal to 72 over the interest rate, and I'll write it as I, so we know that we're writing it here as a number and not a decimal representation here. You can also do kind of the inverse. You can solve this for I and say, well, what interest rate would I need if I wanted my investment to double in a certain number of years? I'll just write TTD, time to double. So for example, if I really needed my money to double so that I could pay some bill or I could retire or whatever, if I really needed my money to double in, let's say, 5 years, then 72 divided by 5 says that I would need to find an investment with an interest rate or a rate of return of about 14.4%, right? And this is approximately that. It's not going to give you the exact answer, but it's going to be pretty close most of the time. I encourage you to play around with this formula and different interest rates and just see how remarkably close your answers you'll get are for a very wide range of interest rates. Now, why 72? Let me give you a 1-minute derivation of this. If our money is doubling, let's just go back and let's look at the continuous compounding formula is probably the easiest way to see this, okay? So our continuous compounding formula says the future value equals the present value times e to the interest rate times time. If our money's doubling, we can divide both sides by present value, and we just get that the ratio is e to the RT. But if our money's doubling, the future value divided by the present value is going to be about 2, right? Okay, so if 2 is about equal to e to the RT, let's take the natural log of both sides, equals r times t. And so if we want to solve this for time, then divide this by r, and there we go, where t is the approximate number of years. I know I've been using n before. What's the natural log of 2, you may ask? Well, the natural log of 2 is about 0.693. 0.693 divided by the interest rate equals t. And here, let me replace this r with I, right? Because what I want to do is multiply the top and the bottom by 100. And you can see what we'll end up with is 69.3 divided by I, which is the interest rate not in its decimal form, will give us the number of years. Now this 69.3 is pretty close to the 72 that's in the rule of 72, but it's a little smaller. So why 72? Why not 69.3? There are 2 reasons I can give. One, 69.3 would be the right number to use if we were continuously compounding, right? So we would want to use a little bit bigger number so that we end up with a little bit higher number of years that we're going to have to wait for our money to double if our money's not continuously compounding, if it's only compounding once a month or once a year, for example. Second, use 72 because 72, this is a rule of thumb, is not meant to be exact, and 72 is a very nicely divisible number, right? 72 is something you can do math in your head with very easily because it's divisible by 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, and 36. So if you had an interest rate of 2, 72 divided by 2, 36. You'd have to wait 36 years for your money to double at an interest rate of 2. But it's also divisible by 3. 72 divided by 3 is 24. So if you had a 3% interest rate, you'd have to wait 24 years, roughly, for your money to double. And again, you're going to get different answers based on how often it's compounded. Okay, just a couple more examples. We're almost done. Instead of calculating the future value, sometimes you need to do the opposite. You need to calculate the present value. So let's just do a couple of present value problems. So we're just going off here off of the general compounding formula, kind of the easy version there. But this same thing kind of works if you're doing continuous compounding or if you're doing multiple periods per year compounding. But if we just take this equation for future value and we solve it for present value, you can see that all you're going to have to do is divide both sides by 1 plus r to the n. So present value equals future value divided by 1 plus r to the n. What are we doing here? Well, we're asking the question, suppose there's some future value that I need, or suppose somebody says, hey, I need to borrow some money today, and in return, I'll pay you back $100 in the future, okay? What would that present value be that you should be willing to lend someone if they promise to pay you back, say, $100 in the future. This is the kind of formula you would use. Another use for it is, suppose I need $100,000 in the future to be able to go to college. How much money do I need to put in the bank today at a certain amount of interest in order so that it will grow to be $100,000 in that future? So that leads us to a problem like number 9. Suppose somebody promises to give me $100 exactly 10 years from now. If I had that money now, suppose what you would have done is invested it in a savings account that compounds interest just yearly, paying 2%. How much is this promise worth, assuming you're 100% sure that they'll pay you off, that this person won't skip town? So just using our formula that we derived up here, present value equals that $100 in the future divided by 1 plus 0.02 to the 10. So $82.03. So that tells you if you had $82.03 and you put it in the bank, earning 2%, then after 10 years, you'd have $100 in the bank account. So it tells you how much that promise in the future, 10 years from now, is worth to you today. Again, we're assuming they actually will pay us that money in the future. Let's do one more problem just to get a feel for how these numbers change as interest rates change. What if exactly the same thing happens except I could invest that money? If I had the money today, I could earn 5% on it. Then the present value today would be $100 divided by 1.05 to the 10th, and that would be $61.39. So that promise of $100 in the future is now worth less to us because if we had the money now, we could earn more on it through time. So there are a couple of different ways you can interpret these present value kinds of ideas. So these examples are pretty simplistic. There are a few ways we could try to make this more realistic. First, a lot of people make multiple different kinds of investments, or they have different alternate investments, and maybe some of these investments are riskier than others. So a complete treatment should want to take those things into account. Also, we're not really certain that people will pay in the future. Turns out that's a fairly easy thing to take into account. For example, let's suppose that we only think there's a 50% chance that this person will pay up in the future. There's an easy way to handle that. The present value would be half of what it is if we were certain they were going to pay, right? Pretty easy to do. So that would be $30-something in that case. Another real world thing, if we wanted to make this more complicated, I'm not going to, but another real world consideration is you're not 100% sure what that interest rate would be for the next 10 years. Maybe it's 2% today, but 2 or 3 or 4 or 5 years from now, it might go up or it might go down. We need some way to think about handling that. And maybe if people ask in a future video, I'll think about talking about that. Here's the thing we are going to do next. Many times, people are going to be either receiving multiple payments. Say, I buy some kind of bond, and this bond that I buy is going to pay me multiple payments. Maybe at the end of every year, they're going to send me $50. How do you handle multiple payments? Whenever you buy a house, you don't just pay everything back at once. You make multiple payments on the loan. And a third example would be, well, what if I don't want to save for college all at once today? What if I want to save for college to where I need to have $100,000 in the bank in 10 years' time? But what I want to do is every year or every month, invest a different amount. So maybe I'll put $100 in the bank today and $100 next week, or I'll put $10,000 in the bank at the end of this year, and then at the end of the second year, and then at the end of the third year. How can we handle those? Well, what we're going to be looking at in the next video are annuities, where we're either making payments or receiving money every year for a certain number of years, and we'll also be looking at perpetuities. Perpetuities is a case where people might be paying you every year from now till the end of time, or at least theoretically, forever. So in video 2, we'll look at annuities, perpetuities, and two things you see in finance classes a lot: the future value interest factor of an annuity and the present value interest factor of an annuity. We'll derive those formulas so that you understand where they come from. I hope you join me next time. And if you have any questions or comments, please leave them in the comment section below. And as always, good luck on your studies, everybody.